Hello, Mr. Colati here. Today we are going to continue our study of probability by looking at the addition rule, which is a bit of a shortcut for solving a probability question. We're going to build the addition rule using some Venn diagrams and a few examples. Now, if you've looked through your textbook, like most textbooks, probability is taught with these kind of traditional sorts of questions and examples. Students are taking physics and chemistry, which ones are taking both. Students are playing on the volleyball and basketball team. They're always sort of irrelevant problems. So a few years back, I took this lesson, I kind of reworked it to address a more real-life problem and a more difficult problem. So case in point, for this example, according to the 2018 Toronto Street Needs Assessment Report, there are 8,715 people living in Toronto without a home. So this was a census taken of all the homeless people in Toronto a few years ago. It was a huge population, right? That's how many times? That's like 7 times the population of our school, people who don't have a house, or don't have a home, don't have a place to live. Of this homeless population, 2,700 suffer from a chronic or acute medical condition, 2,004 suffer from physical disability, 785 suffer from both. So just before we go on, like this is a really useful report for the city because we can document exactly like what the needs are of the homeless population. And there seems to be a tendency sometimes in the city to think of the homeless population as a problem, as a blight, but like the reason someone is living on the street doesn't have a home is probably because of some other reason. Like look, a huge portion of that group has acute or medical condition. So there's some issue that might be preventing them from keeping their home. So there's some really interesting information here and some really disheartening information, but hopefully also some information about how we can help the homeless population. So, okay, let's look at this. Is this data mutually exclusive? Why or why not? Well, hopefully you're remembering back to the previous lessons. If I were to graph this with a Venn diagram, so I have a whole bunch of people who suffer from a medical condition, that's acute or chronic, and then I have a whole bunch of people who suffer from a disability, and some people suffer from both. So when I have a situation like this with overlap, this is not mutually exclusive. Because a person can have a medical condition and a disability. Okay, write down the number of homeless residents who suffer from both a medical condition and a physical disability. Write down, remember, is an easy question. I should be able to find the answer in the question. And sure, there it is right there, 785. So the number of people who have a medical and a disability, the intersection, that is 785. And again, this is very disheartening, right? How hard it must be to function if you have a medical condition and a disability. Okay, so how many residents suffer from a medical condition or a physical disability? So remember, or. This is really the union. That's like a marriage of the two. So that would be adding up all the people in this circle and this circle. Now, what we would have done if we learned this last time is we would have filled in the circles for my Venn diagram. I would have solved the Venn diagram, and then I could just figure out the probabilities from there. But instead of solving the Venn diagram, we're going to learn a new rule. So instead of solving the Venn diagram, I want you to think. What are we really asking for? Well, we're asking you to count all the medical people suffering from medical condition and all the people suffering from a disability. So we need to count NM and ND. But then if I count all the medical and all the disability, I've counted the people in the intersection in this area twice. So I need to then, after adding the two, I need to remove the people who are counted twice. So that is, I have 2,701 people with a medical condition plus 2,004 with a disability minus 785. If I type that into my calculator, I have 2,701 plus 2,004 minus 785. Then I get 3,920. So again, just before we write the rule, look at that. Look at this interesting data. Almost half of the people without a home in Toronto are suffering from either one of these two, medical or disability. I mean, this is a big alarm bell, I think, for the city, that maybe one way we can help the homeless population, reduce the homeless population, is to provide assistance for people with these conditions, or to put more supports in place. So essentially, we've just created the addition rule, which is for non-mutually exclusive events. The number of elements in the union is equal to the number of elements in A plus the number of elements in B minus the number of elements in that are counted twice, that are in the intersection. Similarly, the probability of A union B, it's the same. The probability of A plus the probability of B minus the probability of A intersect B. So that is our addition rule. Well, the first part of the addition rule. And it really just stems from that idea of counting someone twice. Just to note that it only works in this form. So you'll see then some examples. There'll be a tendency to try to rewrite the addition rule your own way, but no, you have to write the addition rule in this form. For example, if you're thinking, okay, if I have A complement union B, remember we did some of these yesterday, we shaded in the weird areas. This is not, you can't just distribute and create your own addition rule. So you can't have P A complement plus PB minus P A complement intersect B. So it doesn't work like that. The addition rule only works if you're finding unions and intersections. Okay, so there's our addition rule. Now we're just going to continue a little bit before we have finished our understanding of it. According to the street needs assessment, of the 8,715 people living without a home, 533 sleep on the street and 7,154 sleep in the shelter. Is this data mutually exclusive? Again, if we think back to when we learned this definition last lesson, we have a bunch of people who sleep on the street. That's 533. And we have a larger group that sleep in the shelter, which is 7,154. When you can't be both, right? You can't sleep in both the street and the shelter on a given night. So this is mutually exclusive data. And you can see, again, we still have, a huge population of people who don't have there's no bed for. So because it's mutually exclusive because you can only sleep in one place. Okay, so now how many homeless residents sleep on the street or in the shelter? So this is that union idea. So before we talk about the addition rule, let's just reason through it. Well, one or the other, well, it would be taking 533 and adding 7,154. We simply add the two events. So that is 533 plus 7,154, which is 7,687. This is a lot easier, this example, because no people are counted twice. We don't have that issue of the intersection. So we conclude then for mutually exclusive events, then the number of elements in A union B is just the number of elements in A plus the number of elements in B. Or the probability of A union B is the probability of A plus the probability of B. That is, there are no elements in the intersection. That set is empty, right? There is no intersection here, like in the first example. So let's just put this in a box. So this is kind of the other half of the addition rule. If you look, this is essentially the addition rule, but the intersection, that subtraction, doesn't happen because there is no intersection. So one key point here, and we're going to get into this at the end of the lesson, if you ever want to prove that something is mutually exclusive, you can use the formulas on this page. They are the only way to verify mutual exclusion mathematically. Because think about it. They're the only way to verify mutual exclusion mathematically. If I wanted to know if two sets are mutually exclusive, I could try using this formula. If I end up with an intersection, I know that they are not mutually exclusive. It's up here. If there is no intersection, if the intersection is 0, then I know they're mutually exclusive. So we'll see an example like that on the back page. So the addition rule allows us to basically not have to draw a Venn diagram. So let's look at this example here. According to the street needs assessment, that same study, Toronto's 8,715 people living without a home, 3,300 have been to the emergency room, and 2,000 have reported an interaction with the police, and 434 have had interactions with the emergency room and the police. Using the addition rule, calculate the probability that a random homeless resident has had these interactions. I bring this up because here's just before we go on to the example, this is a infographic from, I think it's a group that's trying to helps the homeless population, is trying to end homelessness in Toronto, but the cost to society of homeless people is way higher if they're living on the street, if they don't have supports, because you have to pay for all of these things. You have to pay for the police interactions. You have to pay for these emergency room visits. Look how high they are. And the studies have shown that it would be cheaper to Torontonians to pay for a room for every homeless person than it would be to have to carry all these costs as they happen. Paying for hospital time, paying for a shelter bed. So not only is it more socially correct for us to provide housing for people who need it, but it's also economically makes a lot more sense too. So that's something to consider. Hopefully you guys, when you're in power one day, you can help improve this issue. Okay, sorry, rant over. So let's calculate the probability that a random homeless resident has interacted with the emergency room. So if you have emergency room and police, those are the two things we're dealing with here. So the probability of having an emergency room interaction, that is the number of who have had interactions in emergency room, which is 3,312, over the total number of population, which is 8,715. Again, it's permissible to leave the fraction like this. You don't have to reduce. You can turn it into a decimal if you like. Okay, part B. What's the probability that randomly selected homeless resident has interacted with the emergency room and the police? Well, and really means this, right? It's the intersection. And that's very rare. That means you have to have both of these things happen. So if you can imagine the Venn diagram, you're talking about that little intersection point where both circles overlap. So this would be the probability of E and P, emergency room and police interaction, and that was given in the question. 434 have interactions with both over 8,715. Okay, question C. What's the probability that someone has interacted with the emergency room or the police? Well, or means union, right? This is that where I have to add up both circles and subtract out the people who are counted twice. So instead of using a Venn diagram, I can use my formula. E union P is probability of E plus probability of P minus the probability of the intersection, E intersect P. If you want that, there's my addition rule right there. I just copied it from the other page. So now I can sub in my values. PE is 3312 over 8715. Probability of police, we didn't calculate it, but oh, there it is, 2092 over 8,715 minus the people who are counted twice, or the probability of being counted twice, which is right there. This is all common denominator, so I should be able to figure this out. 3312 plus 2092 minus 434. This gives me 4,970 over 8,715. So again, what's the probability of interacting with both of these services? Over half have interacted with these services. And again, this is not really just, but also like a financially really draining. What's the probability that someone has interacted with the emergency room but not the police? So this is, if you want, what's neat about these probability questions, you can convert them from text into probability notation. So has interacted with the police or emergency room, but not the police. So the complement of the police. Now you did this the other day. This is one of, if you can imagine, the Venn diagram, just to help you out here. This is E, let's say emergency room is here and police is here. So this is all of E. Where does it overlap with not P? So not P is everything outside the P circle. So there would be this, I like to call it the crescent, right? It would be everything that's just E, but not P. One way to figure this out, again, if you don't need the Venn diagram, it's the probability of E minus those people who are counted twice. So the probability of being in the E circle minus the probability of being in the intersection. I can sub in my values. This is 3312 over 8715 minus the people who counted twice, so the probability of being counted twice. 3312 minus 434, so I get 2878 over 8715. And finally, the probability that someone has interacted with the emergency room, neither the emergency room nor the police. So this is the probability, we can turn this into math language, not emergency room and not police. And if you can imagine that, that's that. We did this the other day. This is the area, the probability of not being inside either circle, right? Of not having that happen. So one way of figuring this out, if you think about it, well, this is 1, because the shaded area plus the union has to be 1, the total of 1. So it's the 1 subtract this area here, the union. So that's 1 minus, we calculated the union up here, 4970 over 8715. So it's 3745 over 8715. So just under half have had neither interaction. So that's how we can solve a question like this without a Venn diagram. Now, if you wanted to, you could have made a Venn diagram, but eventually you're going to be asked questions where you couldn't even make a Venn diagram. Case in point, let's continue to example below. The probability that a homeless resident identifies as Caucasian is 0.37. The probability that a homeless resident identifies as Indigenous is 0.1. Calculate the probability that a homeless resident identifies as Caucasian or Indigenous, Caucasian and Indigenous. So this is just not trying to prove anything here. I'm just using some data from that report. Sorry, is this mutually exclusive or not? Well, a homeless resident can probably only identify as one or the other, Caucasian or Indigenous. So this is mutually exclusive. You can't be both. Or at least in a survey that's being asked, you probably can't be both. Of course, life isn't usually that cut or dry, but we're assuming in this survey you can only be one or the other. So if I'm asking for or, which is the union, this would be the union of Caucasian, union Indigenous. So if we go back to my addition rule, if something's mutually exclusive, the circles don't overlap. So I just add the two probabilities. So 0.37 plus 0.10, that gives me 0.47. Part B, what's the probability that someone identifies as Caucasian and Indigenous? Probability of Caucasian and Indigenous, the intersection. This would be 0, or at least we think, according to the survey, you probably are checking a box and you can't check both. So, not possible. Because the data is mutually exclusive. I guess we could make a comment that this is a bit of a having to choose one box on a survey. It's probably also going to give you slightly incorrect data because it's forcing something that is not mutually exclusive into a mutually exclusive result. Okay, finally, the last question. So this is what we're building toward, and this is a challenging question because, look, I haven't given you any information. There's no real life problem here at all. I've just given you numbers. I've said the probability of A is this, probability of this, here's the union. Are they mutually exclusive? And this is a real life IB question. Well, remember, I told you, you can prove mutual exclusion using the formulas on this page. If the numbers follow this, then it's mutually exclusive. If the numbers sub in and follow this, then it's non-mutually exclusive. In other words, we're looking at the intersection. If the intersection exists, it's non-mutually exclusive. Doesn't exist, it's down here. So, to prove this, we must use the addition rule to test for mutual exclusion. So we know the probability of A union B is 0.85. Okay, let's look at the probability of A plus the probability of B. That's 0.7 plus 0.2. That gives me 0.9. Okay, now look at this. The probability A plus B does not give me the union. So because, or since, the probability of A union B does not equal the probability of A plus the probability of B, then I know that there's not, I know they are not mutually exclusive. Right? Because if they were mutually exclusive, then the probability of A union B would equal the probability of A plus the probability of B. Because it doesn't, then they're not mutually exclusive. I'm just going to show you on your formula sheet here, probability section. Those formulas exist. So the mutually exclusive events, there's the addition rule right there. Combined or non-mutually exclusive events, there's the formula right there. So you can always test for mutual exclusivity. Okay, that's it for today. Our homework is to tell people out there that we can end homelessness in Toronto and improve the quality of life for everybody. And then it's also to do these questions. When you're doing these questions, you're going to have one that says it's about prime numbers. And my question, if you're asking yourself, well, is 1 a prime number? Well, the definition of a prime number is it has 2 and 2 factors only. 1, like for example, number 7 has the factors 1 and 7 only. 1, though, has the factors 1 and 1, which is only 1 factor. So no, 1 is not a prime number. So that'll come up in one of the questions. It's just something you're going to need to use. All right, good luck with that, and we will see you next time.